इस पार्ट में हम दो रेफरेंसेस को सॉल्व करेंगे और इससे हमें एक तो कुछ प्रैक्टिस मिलेगी कि रेफरेंसेस को कैसे सॉल्व करना चाहिए। अम, और उसके अलावा ये जो दो रेफरेंसेस मैं आपको इस वीडियो में प्रेजेंट करने वाला हूँ, जिनमें से ये पहली रेफरेंस है और ये दूसरी रेफरेंस है। ये दोनों रेफरेंसेस एक्चुअली इनके साथ रिलेटेड जो एल्गोरिदम्स हैं, the algorithms which produce these references, वो हम नेक्स्ट वीक आई थिंक वो देखेंगे। सो सो देयरफॉर दे आर गोइंग टू बी यूजफुल बिकॉज जब हम वो algorithms देखेंगे then I will not have to do this analysis at that time, क्योंकि हमने आज इसको कवर कर लिया। So if you look at this first reference, just looking at it, you can now say something about the algorithm. You can say that this particular algorithm divides the original problem into four subproblems, each of which have half the size. And then to combine their solutions, the overall work that it does within this call of size n is this C of n, C into n. ये O of n work इस स्टेप में होता है। और ये बेस केस है जो हमने यहाँ पे अलग से स्पेसिफाई कर दिया। So again, we will follow the same steps. We draw the tree for this reference, and this is a tree where we have 4 children nodes for every node. So we have the top call of size n, it's 4 children, each of size n by 2. These are each going to have 4 children of size n by 4. So actually at this level, level number 2, I have 16 calls. So I have not shown all of them, but you can see if you count these lines, there are 16 calls here, and each is of size n by 4. And this continues. And then we have the last level where we have all the ones. Now at this point, I want to say something because there has been an assumption that I have been taking in these analyses, and I have not talked about that assumption. जब हम एक्चुअली ट्री बनाते हैं तो आपने देखा कि जैसे जब मैंने मर्ज सॉर्ट आपको दिखाया, साइज 12 की अरे ली थी मैंने उस एग्जांपल में, तो कुछ जो पाथ्स थे वो सेकंड लास्ट लेवल पे खत्म हो गए थे, कुछ बेस केसेस सेकंड लास्ट लेवल पे थे और कुछ लास्ट लेवल पे थे। लेकिन जब भी मैं ये एनालिसिस कर रहा हूँ तो मैं एक फ्लैट लास्ट लेवल ले रहा हूँ, एंड आई एम इमेजिनिंग कि ये एक परफेक्ट ट्री है जिससे कि एनालिसिस आसान हो जाता है। सो यू गेट अ परफेक्ट ट्री व्हेन you're dividing by 2 each time, and you get a perfect tree when n is a power of 2, when n is an exact power of 2. So if you remember, I posted a question on Google Classroom as well, and in that question I said that take n is equal to 256, and then you can easily tell कि total number of calls कितनी हुई हैं एक tree में, because 256 is a power of 2. It's exactly equal to 2 to the power 8. Now if we can take n is equal to 2 to the power k, then the math comes out very clean. So we should, however, remark here that this is a safe assumption. ये जब हम ये assumption लेते हैं तो उससे हमारा जो analysis है उस पे कोई असर नहीं पड़ता, और उसकी वजह बिल्कुल सिंपल सी है। वो ये है कि अगर आप ये कहें, अगर आप ये एतराज करें कि तमाम वैल्यूज ऑफ n टू 2 की पावर नहीं होती, मे बी मेरे जो अरे है उसका साइज 100 है या 100,000 है, so these are not powers of 2. But here is the truth that for every positive number n, there is definitely, if it's not a power of 2, then it lies between two powers of 2. Right? So there is going to exist a k such that this n, if it's not k, if it's not 2 to the power k, then it lies between two powers of k. Okay, so for some k, it's going to lie like this. So for example, अगर आप 100 का example ले लें, 100 is not a power of k, but it lies between two powers of k, namely 64 and 128, 2 to the power 6 and 2 to the power 7. So if I take 100 and I take log of 100, the answer to that is 6 uh, after taking floor. So I'm just away by 1, right? तो मतलब अगर मैं एक n का log ले रहा हूँ, अगर मैं assume कर रहा हूँ कि इस tree के exactly log n levels हैं, तो मे भी हो सकता है कि इसके log n levels ना हो, log n plus 1 हो. Okay, but that's okay. I can live with that. A difference of 1 is okay for me. So if we imagine n to be power of 2, our analysis will be off by plus 1 in the terms of log, which is okay. Okay, so our analysis is safe. So from now on, I am always going to take this assumption that n is a power of 2. Okay. In some cases, I can even take the assumption that n is a power of 3 if I'm dividing by 3 each time. So these are just simplifying assumptions which do not disturb the analysis. Okay, they do not hurt the analysis. So this was a bit of a detour just to explain to you कि ये assumption हम ले सकते हैं और इससे हमारा analysis या math जो है वो clean हो जाता है. So now let's come back to our recurrence. So in this recurrence, we just saw that we have a branching factor, meaning number of children at each time of 4. So अब हमने वही काम करना है कि इसका टोटल काम निकालने के लिए हम पहले लेवल बाय लेवल वर्क निकालेंगे. So पहले लेवल पे अगेन एक सिंगल कॉल है ऑफ साइज n, so there is work, total work of c into n. Second level पे there are 4 calls of size n by 2 each. Now each of these calls is taking c into n by 2 work. Okay, according to this recurrence. If I have n by 2 here, then the work on that call is c into n by 2. So there are 4 of these at this level. That would mean c into 2n, right? So we get 2n total. And in the next level, 16 calls of size n by 4 each. Each of these calls is taking cn by 4 work. So this is c times 4n, right? And now you can guess the pattern. In the next level, which I have not drawn here, there are going to be 32. Actually, no, there are going to be 64 problems, each of size n by 16, I think. Yeah, n by 16, and yes, so you basically have 16 problems here, right? And each is going to have 4 children, so yes, 64 problems. So what's going to be the um, overall work in this level? Why don't you pause the video and answer that question? Right, so there's going to be a total of 64 calls, and the size of each call is actually n by 8. So you get a total of C8n here. And this continues, and you can now see the pattern. The terms C and N are the common terms, and the factor that's increasing is this factor of 2. And in the last one, obviously, you have n calls. And so essentially in the last level, so what's going to be, the factor of 2 that's here at this level? So in the last level, actually, they're not n calls, but at that last level, there are each call is taking C work like this. All of them are base cases. So how many of them are there? Again, C and now 2 to the power. And since this tree has log n levels, okay, 2 to the power log n and n. Okay. Now, why does this tree have log n levels? Because इसमें भी अगर आप देखें तो हर लेवल पे जो प्रॉब्लम्स का साइज है वो हाफ है from the previous level. So how many such divide by 2 operations before we get to the level with one size? Well, that's log of n. So always remember that this height of the tree depends on the factor that's dividing the problem, and that is 2 in this case. So this is just log 2 base n. Sorry, log n base 2. राइट, सो ये वो सीरीज है जब आपको, अब ये आपको हॉरिजॉन्टल टर्म्स मिली हैं और अब आप इसको ऐड कर देंगे वर्टिकली to get the overall work. Let's do that and see what happens. So when we take all these terms and add them together vertically, this is the series we get, which is our geometric series in this case. यहाँ पर मैंने C और N को common ले लिया and this is the geometric series. And now we sum it. So let me this time just show you the formula for the geometric series. This is the formula for geometric series. This is a geometric series with k plus 1 terms. This first term is the one where the ratio of where the power of the common ratio r is actually 0 और उसके बाद वो common ratio बार बार multiply होती है. So this is the formula for that. और हमारे केस में a is 1, right? R is 2, and k is log n. Okay, we also begin from 2 की power 0, and we go all the way to 2 की power log n. So we can just directly plug these values into this, right? So if we do that, in fact, you can just do it yourself. Plug a is equal to 1, r is equal to 2, niche 1 minus 2, that's minus 1, and then so we can just invert this. So this will be like 2 to the power log n plus 1 minus 1, and again we just get 2 to the power log n plus 1. Minus 1 को हम ignore कर देते हैं. So that's going to be about 2n, 2 times n. So this total will turn out to be 2 times c n square. Okay, in other words, this is just O of n square. So this algorithm, which is dividing the original problem into 4 sub-problems and then taking linear time to combine their results, is taking overall n square time. Now I want all of you to be able to do this systematic analysis. और इसमें सिर्फ एक चीज है जो अहम है, और वो ये है कि आपने इस ज्योमेट्रिक सीरीज को, ज्योमेट्रिक सीरीज का जो फॉर्मूला है उससे उससे यूज करके तो आपने उसको सम अप करना है. अगर आप इसका नाइव सा एनालिसिस करेंगे तो देन यू कैन जस्ट look at these things and you can say, oh, this is, I don't know, n square log n or something like that. But no, when you count them together, it's not n square log n. Even though they are log n levels, when you sum up these terms, तो ये जो 2 के factors हैं, ये overall sum करके over, there are log n of these, obviously, log n plus 1 of these terms. But when you sum them using the geometric series formula, you get just an n out of this, 2n. And overall multiplied here, it becomes O(n) square. So this was for this particular recurrence. What happens when there is a slight change in this recurrence? That's like our next recurrence. Okay. The only difference between this one and this one here is that we have one less recursive problem. So we're saying that there is some algorithm which divides itself into 3 child problems of size n by 2 each, and then combines their result in linear time. Okay, by the way, some of you may be confused that how can this happen even in this one, कि आपके पास हाफ साइज की 4 प्रॉब्लम्स आ जाएं, हाफ साइज की तो 2 ही प्रॉब्लम्स आनी चाहिए एंड सो ऑन. बट ऐसा नहीं है. हम इस एल्गोरिथम को एक्चुअली नेक्स्ट टाइम देखेंगे भी, और आप देखेंगे कि ऐसा हो सकता है समटाइम्स कि आपकी जो सेम ही प्रॉब्लम है वो ओवरलैप कर रही है. मतलब फर्स्ट हाफ, सेकंड हाफ, फिर मिडिल हाफ भी आपने लिया हुआ, फॉर एग्जांपल. So that can happen. So therefore you can have these sort of 4 times half the problem, or 3 times half the problem. So you'll see this algorithm in the next lecture. So for this recurrence, if we, this thing is called the branching factor, as I said last time, the number of children you're going to have for each node. But this thing is the same as in the previous recurrence. We are still dividing every problem, like actually dividing the problem size by 2 in each child call. And this thing is also the same as in the last recurrence, that we're combining the solutions in linear time. So what is the overall impact of this change of the branching factor on the running time? So again, we will go through the systematic analysis. of this recurrence and see what happens to the overall running time. In fact, I will encourage you कि आप यहाँ पर इसको pause करें वीडियो को और खुद से ये सारे steps कर लें पहले एक दफ़ा। आप horizontally हर level का time accumulate करें, फिर vertically इसको add करें, series को sum करें using the geometric series formula that I just showed you, and find the final running time. And then I'll do it. Okay, so I hope that you have solved this, attempted to solve it. So, well, let's again go level by level. So in the first level here, according to the recurrence, size n की problem को cn work चाहिए होता in that step here. In the second level, 3 total problems. Each problem is of size n by 2, and each problem in itself needs cn by 2 work. So the total work in the second level is 3 cn by 2, right? So I'm just going to write it like this: 3 by 2 c and n. Okay, this looks nice that the numbers are in the beginning and then c and n. Now in the next level, there are how many problems? Well, branching factor 3 here, so there's actually going to be 9 problems, and each of them have size n by 4, and each single problem is going to take time cn by 4. So that means I can just write it concisely like this: 9 by 4, right? And c and n. So you can again see that this is a geometric series. I will always get a geometric series, but in this geometric series the ratio is different. Okay, it's not like 2, which we have been getting so far. In the case of merge sort, the ratio was just 1, right? It's just like n n n, c n c n c n. But in this case the ratio seems to be 3 by 2. So this is 3 by 2, and then this is 3 by 2 square. Actually, in the next step, and you can confirm this, like there is 9 into 3, I think 27 problems, each of size n by 8. Okay, so what you have here is 27 uh, by 8. Okay, so it's just 3 by 2 cube, right? And cn. And this continues, and like in the last one, again, this 2 is again that same 2. So the number of levels hasn't changed. अभी तक हमने एक ही रेफरेंस देखी है जिसमें वो जहाँ हम मर्ज सॉर्ट में n by 3 साइज की प्रॉब्लम्स बना रहे थे जहाँ पर हमारे पास नंबर ऑफ लेवल्स log n base 3 थे. अदरवाइज जितनी भी रेफरेंसेस हमने देखी हैं उसमें हम ये LGN log n base 2 लेवल्स हमें मिल रहे हैं बिकॉज साइजेस हाफ हो रहे हैं and there are log n base 2 divisions required to get here. Now this is just 3 by 2 to the power log n. That's the last term of the geometric series, and c into n. Okay, so this is basically level by level by level. So you shouldn't get intimidated to see this fraction here because it's just a number. It's just a real number. Like 2 was a real number, 1 is a real number. So this is just a real number. It's just a fraction. And you just have a geometric series with a slightly different looking ratio. And you're going to add all of this vertically now. And you're going to apply, yeah, this formula we talked about earlier. Now in this case, r is 3 by 2. Okay. Last time the nice thing was that r was 2. So, you know, 2, and then there was this power log n, 2 की power log n. So अगर आप 2 की power log n लें तो you get n again. Now here we have this r, and in the denominator again I will get -1 by 2, which I can flip these two, so that will become 1 by 2 in the denominator, so then it will just multiply here and just get a 2 here. So in fact, why not take the sum here and then uh, plug it back? So let me write down this series, and then we work out the sum for the series. So this is your geometric series, right? If you take C n common, this is the geometric series. The only difference here is कि 2 की बजाय 3/2 की पावर्स है, और जो लास्ट टर्म है वो है 3/2 की पावर log n. So now we can just use this formula, okay, and plug in the values. Let me just reduce the size so that we can see both these things at the same time. So this is the series, and this is the formula we're going to use to solve it, right? And well, I think we can just do it step by step. So Cn तो बाहर ही है, right? और ये जो चीज इसमें ये जो geometric series है, यहाँ पर हम ये अब values plug कर लेते हैं. तो let me plug in these values and then we discuss impact of doing that. So this is what I will get if I plug in these values. मैंने यहाँ पर a को 1 लिया है जो कि 1 ही है. This is a, and r is 3/2, and I have just flipped, rather than 1 minus r to the power k plus 1, I've just written r to the power k plus 1 minus 1, and I've also flipped this r minus 1. So this is going to give me 1/2, and so there's going to be a lot of constants in here, right? This answer, for example, is going to be 1/2, which means this 1/2 in denominator, तो यहाँ 2 ने multiply करना है, और फिर ये जो -1 है ये भी एक constant है. फिर ये जो 3/2 की power log n plus 1 है, इसका मतलब है 3/2 की power log n multiplied by 3/2. So there's that constant 3/2. Now, rather than working with all those constants, there is a nice trick that you can use, because in the end, we are just interested in the asymptotic running time here. So what you can say is, you can say that, well, all of that uh, will just be absorbed into another constant C prime. इस constant में C भी शामिल है, और वो बाकी सारे constants भी शामिल है. And multiplied by n, and the thing that we are interested in is the thing which depends on n, okay, which is not a constant, and that is 3/2 की power log n. Okay, that's the term that we're actually interested in. Now you could have been more careful, and you could have said, "Nahin, I want to work out all the constants." But even if you do this, this shows that you have a knowledge of asymptotic notation, that yes, of course, I can always find a constant C prime such that this entire thing is less than or equal to that, and ignoring those constants. This comes from our knowledge of asymptotic notation. So what happens to this? Now this thing, I can just focus on this fraction, okay? And let's see what this fraction gives us, okay? So this is what we get, right? 3/2 की power log n is just 3 की power log n divided by 2 की power log n. But 2 की power log n, and this is log base 2n, that is just n. And that n is going to cancel out this n, right? So all we are left with is a constant multiplied by this. और यहाँ पर भी एक extra rule of logs है जो कि use होगा. वो rule of logs ये है कि if you have a and log base something, let's say log base 2 ही ले लेते हैं, base well, let's call this x, right? So in general, if you have this, then this is actually equal to, if you replace the base, okay, so this is x, and this is log base same rahegi, and then a. Okay, so these x and a, they can be switched. This is another a rule of logarithms. You will have to look it up in your calculus book. So here, if I replace it, so what we're saying is we have n log 3, and this basically is log of 3 to the base 2. You can actually use your calculator, compute this number, because both of these are actual numbers, right? So what is log of 3 to the base 2? Log of 4 to the base 2 is 2. So this is a number less than 2, right? Actually, you should find out what this number is. So this number actually turns out to be 1.58. So our algorithm, whatever this algorithm is that has this recurrence, has a running complexity of running time of 1 n to the power 1.5. So it's like O of, because we also have the C prime, right? I missed the C prime here. So this is just O of this thing, big O of this thing. Okay. Now this is an improvement. This is a major improvement. O of n square, if you plot it for large n, will be quite way above uh, n to the power 1.58. So this is a big improvement. In fact, हम देखेंगे next time एक algorithm जो कि start करेगा from here using this recurrence. उस वक्त उसकी complexity of n square होगी और फिर उसमें clever maneuver करेंगे जिसको करने के बाद उसकी recurrence ऐसे हो जाएगी और उसका running time ये हो जाएगा. It's a huge improvement. So again, the lesson here is that there are two things that determine uh, the geometric series. First of all, there's always going to be a geometric series, and the overall time will be determined by whatever we get as the result of the sum of that series. But there are two things which are changing the running time. Given that this work per level is the same, just like in this recurrence and this recurrence, the work per level is the same. The things that impact are this branching factor here and this number, which is like the deviation factor, meaning how much of a reduction in data is happening in every call. So इससे आपकी जो ये रेशो है ज्योमेट्रिक सीरीज की वो डिटरमिन होती है. जैसे यहाँ पर आपकी रेशो 2 आ गई थी तो आपका ओवरऑल वर्क n स्क्वायर तक चला गया. यहाँ आपकी रेशो r जो है वो 3/2 आई तो आपका काम कुछ नीचे रहा, यहाँ तक आ गया. मर्ज सॉर्ट में ये रेशो 1 बन गई थी. और जाहिर है अगर ऐसा भी हो सकता है कि यहाँ पर किसी एक स्टेप में आपको n से ज़्यादा n स्क्वायर काम लग रहा हो, मे बी कंबाइन आपका n स्क्वायर टाइम ले रहा है, तो फिर ऑब्वियसली वो एक अलग चीज़ होगी, वहाँ पर ये चीज़ n स्क्वायर हो जाएगी एंड दिस n स्क्वायर इज गोइंग टू कम हियर and it's going to have an impact too. So in your homework, I will put 4 or 5 recurrences that you will solve and you'll get a good practice of how these things work. So this was some practice with recurrences, and now I'm going to move forward and present another another divide and conquer algorithm, which I think will be extremely interesting for you because the problem that we're going to discuss is a simple problem, but its divide and conquer algorithm is very clever and very elegant. So we will have a look at that soon.